All right, here's your homework video on inverses. So if you want to do your homework with me, you can. If you want to do your homework first and then watch the video to see if it matches, you can also do that. So determine whether the relations are one-to-one functions or not. This is what's called the horizontal line test. If I can draw a horizontal line and it hits it at more than 1 point, it is not an inverse. There is no inverse. So are these one-to-one functions? Can you draw a horizontal line and hit the graph at more than 1 point? So no, not one-to-one. Look at this one. No matter where I draw the horizontal line, it's going to only hit at 1 point. So off the graph, we're using what's called the horizontal line test. Here again, if I draw it, it's only going to hit it at 1 point. So those are one-to-one. This one fails because you can draw a horizontal line and hit it at more than 1 point. All right, determine if the function has an inverse. If it does, then find its inverse and state any restrictions in the domain. So first of all, this is a line. There's no domain restrictions. Next, to find the inverse, we're going to inverse x and y. So we're going to write this as x equals 3/4 y plus 3. Then we're going to solve for y. So inverse means the domain and range has been inversed, or the x and y have been changed, switched. All right, solve for y. So the inverse of adding 3 is to subtract 3. And the inverse of a fraction is its reciprocal. So when I do the reciprocal, y is by itself. The symbol for inverse is that little -1. And you don't need to distribute. That's fine. 4/3 x subtract 3 is a great answer. It's still a line. It's all real numbers. There's nothing that would make it undefined or imaginary. Number 5. First of all, is it one-to-one? So the first answer is no, it is not one-to-one. And so why is it not one-to-one? Well, the big indicator is an even exponent. An even exponent where both ends go up is an indicator that it will fail the horizontal line test. If one end goes up and the other one goes down, it's going to pass. So it fails the horizontal line test. And again, the big indicator is the even exponent. 6. Rational is a one-to-one. So when you draw a rational, it's okay. It passes the one-to-one. So now, how do I find its inverse? So step 1 is I inverse x and y. So I make it, instead of y equals, it's x equals, and it's 1 over y plus 2. Next, I'm going to solve for y. So the first easiest step is actually to do the reciprocal. So the reciprocal of x is 1 over x. And the reciprocal of 1 over y plus 2 is y plus 2 over 1, or just y plus 2. To get y by itself, you subtract 2. You do not need to get common denominators. It's fine the way it looks. The symbol for inverse is still a little -1. And you found its inverse. Is there anything x cannot be? Well, to begin with, we have to look at both. So we have to look, what can't it be to begin with, and what can't it be at the end? So first, when I do the inverse, what can't it be? Oh no, I'm looking at the composite. Here, to do the inverse, just look at the end. What can't it be at the end? X can't equal 0. That is from this denominator. Do you notice that x can't equal -2? That means the range would be y can't equal -2 for the inverse, because the x and y have been inversed. So y can't equal -2. That comes from the function in the denominator. X can't equal 0. That comes from your answer. 7, cube root. An odd root is fine. All works going across. So we're going to start with x equals the cube root of y plus 7. Take away 1. Now we're going to do the work to get y by itself. What's the inverse of subtracting 1? We're going to add 1. The next, we're going to undo the cube root by cubing both sides. The power and the root undo each other. And then the last step to get y by itself is to subtract 7. So, what's the symbol for inverse? A little -1. And it's x plus 1 cubed subtract 7. And again, the domain is all real numbers because it's a cube function. And an odd exponent is all real numbers. All right, 8. Oh, it's an absolute value. So what is the picture of an absolute value? It's a V. It fails. Nine. 2x plus 5 over x subtract 7. This is going to take a little work, but we can do it together. So x equals 2y plus 5, y minus 7. It will not help me to do the reciprocal. So my next step is actually to undo the fraction. So I'm going to multiply both sides by y minus 7. On the right, I have 2y plus 5. On the left, I'm going to distribute the x. So x times y and -7 times x. Next, I'm going to identify the terms that have a y in it. So x, y, and 2y, they're the only two terms that have a y in the term. They need to be beside each other. So I'm going to write x, y, but I'm going to subtract 2y so they can be beside each other. If a term does not have a y in it, it needs to be on the other side. So what I'm going to do is I'm going to add 7x to the other side. Because I separated them, I can now factor out the y, and I have x subtract 2. And then I'm going to divide. So once I factor out the y, it becomes easy now to get y by itself. So the symbol for inverse is that little -1. So it's 5 plus 7x over x subtract 2. Look at the denominator. What can x not be? And the answer is x can't be 2. Turn the page. Find the inverse of each function, state any restrictions in the domain, and then verify graphically and algebraically. Well, here we go. Step 1, x equals y minus 4 over 3. To get y by itself, I'm going to multiply both sides by 3, and I'm going to add 4. So there's my inverse. I'm going to put a little -1 there. There is no domain restrictions for either one. It's all real numbers. So to verify graphically, I'm going to graph this. Now, there's like a difficult way. If I write it as mx plus b, that's going to be a headache because you have fractions and so on. Just pick two numbers. So the two obvious numbers I'm going to pick are positive 4. That gives me the answer 0. And I need one more point, or the slope. And the slope is 1 over 3, so I can do that. So from this, I can go up 1 and to the right 3, and then draw my line. Now I'm going to draw the inverse on the same graph. Now the inverse on the same graph is this. Now this one doesn't have the fraction, so it's a lot easier. So I'm going to start at positive 4 and then go up 3 and to the right 1. And again, I'm going to draw a line. Now I'm going to do this one in, oh, it doesn't matter. I'll do it in black. And then I'm going to put a red pen for y equals x. So, how to verify graphically if they're inverses is you draw the line y equals x, which means you start at 0, go up 1 over 1, and then draw a line. And does this one, when I draw the line y equals x, probably should have went through the corners, right? I don't know if it's a 10 by 10. All right, so there's the line y equals x. If you folded over y equals x, would this fold over on top of this, and would this fold over on top of that? Are they symmetric around this red line? And if you look carefully and fold, as accurate as I'm trying to be, one would fold over to the other, one would fold over the other, and yes, it's been verified using graphs. Now, how do you verify algebraically? Well, algebraically, if you take an inverse and you plug it into its function, it always simplifies to x. So I'm going to do a composition. So I'm going to take the function, which is x subtract 4 over 3, but instead of x, I'm going to do a substitution. I'm going to plug in the inverse, which is 3x plus 4. Can you do the algebra and see if it simplifies to x? So 4 take away 4 leaves me with 3x, and then 3 divided by 3 gives me x, and they are inverses. So I can find the inverse. I understand that the line y equals x, an inverse and its function reflect over it, and I understand the composition, where if I substitute one into the other, in fact, the order doesn't matter. You could plug the function into the inverse, and the same thing would happen. That you do the algebra, it simplifies to x. All right, let's try it again. Number 11. So step 1 is, can you find its inverse and graph both? So this will be interesting, a good review. So if I want to find its inverse, I'm going to start with x equals negative 2 y subtract 1 cubed. Now I'm going to try to do the work to get y by itself. So I'm going to divide by negative 2. How do I undo cube? Is I cube root both sides. So this is going to be cube root. So I have the cube root of x over negative 2 is equal to y minus 1. And then you have the cube root of x over negative 2 plus 1. Right? You add 1 at the end, and that's the inverse. It's a cube root, so again, it's all real numbers. So let's see if we can graph this or not. I know this looks intimidating, so we'll figure it out, I promise. So the first one, I want to recognize h and k. So h is positive 1 and k is 0. So can you find positive 1 and 0? Then all the x's we're going to add 1, and all the y's we're going to multiply by negative 2. So I'm actually going to do that right here. So 0, 0, 1, 1, 8, 2. No, 0, 0, 1, 1, 2, 8. The other way around. And I'm going to transform them. So 0, 0 became 1 and 0. The next one, add 1 and it's 2. 1 times negative 2. Here's 1. 2 plus 1 is 3. 8 times negative 2 is negative 16. That's going to be off my graph. But 1, 0, and 2, negative 2, I can definitely do. How about the other way? What would happen if I had negative 1 and negative 1? Add 1, that's 0. And then negative times a negative makes it 2. So 0 and 2. The last one is going to be negative 2 and negative 8. So if you add 1, that's negative 1. And again, this will be way off my graph. A negative 8 times would be 16. So you can get a sense of the picture of this cube root, or cube function, I mean. Now, how would I graph the cube root? Well, do you see all these points we came up with? If they're inverses, the x and y can be flipped. So if I plug in 0, the answer should be 1. So if I plug in 0, is the answer 1. So 0, 1 is on my graph. That means flip this one. So what's the inverse then? So again, the inverse here, every point you flip. And obviously the last points won't be on our graph. But I can find negative 2 and positive 2. I can find 2 and 0. And do you remember the picture of a cube root? So connect the points together. So notice the 3 points are connected with a long S connecting it. If I draw the line y equals x, if I draw the line y equals x, if I fold one, would it fold on top of the other over that line? So can you see one would fold over on top of the other if you can visualize it? So we verified it graphically. How do I verify it again? How do I verify it algebraically? Is I do a substitution. So I take the inverse and I substitute inside the function. So the function was -2, but now instead of x, I'm going to put in the cube root of x divided by -2 plus 1, and then I have a subtract 1, and I cube it. So first, first 1 take away 1. Yeah, going one way, it's a lot more challenging. But I can do it here. So, one take away 1 leaves me with the cube root of x over -2 cubed. I don't know what I did wrong here. Cube root. Add 1 at the end. So these cross out. The cube root of x and so on, that's just x. The challenge is -2 cubed and -2. It's not going to give me what I want to be able to divide out. I'm thinking, what am I doing algebraically? You can also go the other direction as well. And so I feel like I'm stuck in this direction. I'll come back to it and think about it. So the inverse and the function. So if I start with the inverse, which is the cube root of x divided by -2, if I plug in the -2 x minus 1 cubed for x divided by -2 plus 1, so when I go, oh, and there's a plus 1 with the -1. So the -1 and the plus 1 go. The cube root of this is 2, and it leaves me with x. What's in front of all this? Cube root of this plus 1. The 2's cross out, the 1 minus 1's go, the cube root and root leave me with x. Here, I'm still looking at this one, the cube root of x over -2. I know what I did. So, it's the cube root of x over -2, and the cube root covers the whole fraction. So when I go plus 1 take away 1, they're gone. The cube root and the cube, they undo each other, the cube root and the cube. So what you're left with then is -2 x over -2, and that simplifies to x. Man, I totally messed that up in my head, but I got there. All right, let's try 12. We can do better. I can do better. Now I'm going to tell you that when you graph rationals and the inverse of a rational, it is looking messy on the graph because there's lots of asymptotes and curves going on here. Okay. I can still do this. X equals 3 over y plus 4. I'm going to do the reciprocal. I'm going to multiply by 3 and then subtract. So I have 3 over x subtract 4. That's my inverse. So I'm going to graph both. I might use a pencil to use like for asymptotes. So for the first one, the asymptote is at -4. And 0. So the good news for both the horizontal, this one's at -4. So for this one, there is no x-intercept, but there's a y-intercept at 3/4. If I plug in a number that's less than -4, like -5, gives me the answer -3. Now for the second one. So the second one, it can't be 0. For this one, the horizontal's at -4. We have a point at 1 and -1. And then on the other side, if I plugged in -1, I get -7. I told you it would look a little confusing. Those that feel like, wow, that looks really artistic, I appreciate you. Then, if I draw the line y equals x, I want you to notice that one would fold on top of the other. So if you folded the sheet, one would fold on top of the other. Man. All right. Let's do the substitution. I think this substitution would be a little easier. I hope so. So instead of x, I'm going to put in 3 over x minus 4 plus 4. So -4 plus 4 is 3 over x. And then you multiply it times the reciprocal. And then the 3's go and you're left with x. So we verified it algebraically. We looked at the graph, for goodness sakes. Here, x can't equal -4, and here, x can't equal 0. And we did our best to try to understand the graph and the algebra behind it. All right, one more. Number 13. So first, do you know how to find this? So the square root does have an inverse. The square doesn't. So we're going to write this like this. We're going to add 7. Then we're going to square both sides. We're just going to leave it like that. We're not going to expand it. So x plus 7 squared. And then the last step to find the inverse is we're going to subtract 2. So our h and k, -7 and -2, that's going to help us graph it. So here we have -2 and -7. -2 and -7. Then, if we transform the points, so we have 0, 0, 1, 1, and 4, 2. So 0, 0 becomes -2, -7. We're going to subtract 2 and subtract 7, so we have -1 and -6. We're going to subtract 2 and subtract 7, so we have 2 and -5. So there is the square root. Now, when I draw the parabola, I got to be careful. So I have -7 and -2. I'm going to take these points and I'm going to flip them. So the next point that would be on my graph would be -6 and -1 and -5 and 2. Now I'm not going to draw the full parabola. I'm only going to draw this part of the parabola because that's the part that matches the square root. Remember, it's half a parabola. So this is the half of the parabola that would match it. If I did the full parabola, they wouldn't match. So the inverse of the square root is half a parabola up, not the full one. And then as I go through and draw the line y equals x, do you see how if you folded one, it would fold over the other? Exactly. They're reflections over the line y equals x. Algebraically, I'm going to do the substitution, where I take the inverse and plug it into f to see if it equals, x, when you do the algebra. So we started with the square root of that. Now I'm going to plug in my inverse, which is x plus 7 squared minus 2, and I want to see if this simplifies to x. So negative 2 and plus 2 leave me with the square root of x plus 7 squared minus 7. The square root and the square undo each other, so I have x plus 2 because they're inverses. So I have x plus 7 take away 7, and then 7 take away 7 leaves me with x. So do I understand that a function and its inverse reflect over the line y equals x? Do I understand that when I do a composition of a function and its inverse, a substitution, that when you do the algebra, it should always simplify to just x? Those are the properties of inverses. Awesome job doing your homework with me. I'm proud of you. Mr. G Math. Over now.